welcome to my presentation on an introduction to fractional calculus. Basically, we're just going to talk about operators that behave differently depending on their semi-group characteristics, and we'll be looking into the interpolation formula of these operators. So the two words that I mentioned here that are important are interpolation formula and semi-group. So an interpolation formula is a result of applying an operator successively. Okay, so the result can be obtained recursively, and a semi-group is a mathematical structure which is similar to a group, not in the mathematical sense similar, but similar in the linguistic sense, where it satisfies the axiomatic scheme of having closure, associativity, an identity, and an inverse element. Okay, but what makes it a semi-group is the fact that the inverse element is conditional. It has an inverse element depending on certain characteristics. Okay, so we mentioned that the derivative and the integral operator are not necessarily left or right inverses of one another. Okay, if we study the consequences of interchanging these two operators, what we're obtaining is the different formalisms of the fractional calculus. Okay, so if we study the non-integer application of these operators, we're going to get a different interpolation formula for these operators. Okay, so the two main formalisms we're looking at is the Riemann-Liouville and the Caputo formalism. There are others, but we'll restrict our attention to the Riemann-Liouville formalism. Okay, so just to contrast the two formalisms that we're going to be studying, the Riemann-Liouville formalism basically gives rise to simpler formulae that behave in a better way so that we can use it for analytic methods, for solving, for example, extraordinary differential equations. The Caputo formalism gives rise to formulae which in a sense expand and are more appropriate to solving numerical problems in the fractional calculus. So we mentioned that the Riemann-Liouville formalism takes the derivative operator on the left of the integral, and the Caputo formalism takes the derivative on the right of the integral. Okay, this will also become much more apparent in the details of the definitions as we continue. Okay, so the first definition we're looking at is the factorial function, which is defined for a natural number n, okay, as the product up to n starting at k equals 1. Okay, so it's the product of the naturals up to n starting at k equals 1. And the gamma function is just a extension of the factorial function related to the factorial function by this formula gamma n equals n minus 1 factorial. Okay, but it's better defined as the improper definite integral below. So the beta function does not appear often in the fractional calculus, but it is useful in concluding results in proofs of the fractional calculus. The first encounter we actually have with the fractional calculus is the Riemann-Liouville definition of the non-integer order integral. Okay, so that is defined on the finite closed interval on the real axis. Okay, so the left-sided and right-sided Riemann-Liouville fractional integrals of order alpha, a real number, is based at a and b respectively, is defined in these integral forms. Okay, notice here that a is the lower bound on the first integral, where x is greater than a, and b here is the upper bound on the second integral, with x being less than b. Okay, our next definition is the Riemann-Liouville fractional order derivative operator of order alpha, based at a and b also respectively, and they are defined by these equations. So it's important to notice here that the integer order derivative is applied after the non-integer order integral. Okay, so this m is the ceiling of alpha, which is the next greater integer after alpha. Okay, so notice again we have that the integer order derivative is applied after the non-integer order integral. Okay, our definition for the derivative also contains an integral, which makes this derivative operator a non-local operator. Okay, so that's very important stuff. Okay, our next definition is the Caputo derivative operator, just to contrast it with the Riemann-Liouville operator and to mention more about that on Taylor series. So notice that the only difference with this definition is that the integer order operator and the differentiation operator is applied to the function first, and then we apply the non-integer order integral operator. Okay, what's interesting is that since the integration operator is applied second, it could give rise to some transient terms, which gives us a good clue of how we could define the fractional Taylor series. Okay, so just a little bit about notation. If we write the 1/3 derivative of f, we are forced by the Riemann-Liouville definition of the derivative operator to first write the non-integer ordered integration to the function, and then we apply the the integer order derivative to the function. What I mean by negative exponent on the derivative operator, that corresponds to integration. Okay, so it's also interesting because it avoids the computation of the gamma p, where p could be the complex pole of an analytic continuation of the gamma function. Okay, which then makes our fractional derivative a well-defined operator. Okay, so Lacroix used the Euler's gamma function and this result, the gamma of a half, which is equal to square root of pi, to deduce the semi-derivative of t and t to the 0. Okay, so what I mean by semi-derivative, I mean the half-order derivative of a function. Okay, so how he did this is by first considering the general case where alpha is a real number and lambda is a complex number, and he applied the alpha order derivative to a power function t to the lambda by using the Riemann-Liouville definition and quickly arriving at an interpolation formula. Notice that the result is independent of m, and so if you substitute 1 and alpha is a half, then you obtain the semi-derivative for c. Interestingly, applying the semi-derivative again, we obtain the expected result, this full derivative of t, which is 1. Okay? To compute the semi-derivative of a constant function, we use the same interpolation formula, but we also rely on the linearity of the non-integer order derivative and the linearity property for the limits. So we apply the limit as lambda tends to 0, and we evaluate this interpolation formula with the limit and the constant being pulled out in front. So we obtain the result easily as well. Okay, we've used these properties, the linearity and composition properties, but we've not yet seen them. So let's quickly take a look at that. L1 and L2 here is the linearity property for the integral operator of non-integer order and the derivative operator of non-integer order respectively, and C1 to C4 are the composition properties for the integral and derivative operator. So C1 is the composition of integral to the order alpha and integral to the order beta. So what we're saying here is that we can combine their exponents and we can interchange the order and expect the same result. Okay, the same is true for the derivative operator, and the same is true for the derivative first, as long as it is greater order than the integral operator. And C4 is true only if the transient terms vanish, which means in this case this, you can see, resembles the semi-group property once again. Okay, so L1, which is the linearity of the integral operator, follows from the definition of the operator and also makes use of the integer order integration operator. So L2 is the derivative operator property, linearity for the differentiation operator, and so basically follows from the previous result L1 and some integer order differentiation operators. C3 is the derivative first property, where it motivates the Riemann-Liouville formalism. C4 motivates the Caputo formalism with the integration applied second. Okay, and so we discussed the proof outline for C1, which is the integral to alpha and integral to the beta. If we compose these results, we could write them using the definition of the Riemann-Liouville formalism. We get the double integral. Okay, and then we integrate over the region R, expressed as this set. So if we change the order of integration, this set can be transformed into R prime here. Okay, and so if we make the change of variables and manipulation of the beta function, almost immediately after a couple steps produces the desired result that we may exponentiate these orders. So we mentioned that there are other formalisms, for example the Gruner-Lethnikov formalism, which develops the fractional calculus from the approach of defining the fractional order derivative, and from it the fractional order integral follows. So how they do this is by considering the classical definition of the limits of the difference quotient to define the first derivative, and so recursively after n differentiations they obtain a derivative formula, but this is still of integer order. So to even generalize the result more, they replace the binomial coefficients with the corresponding gamma coefficients, and the upper limit of summation is replaced with t minus h over h, which tends to infinity as h tends to 0. Okay, so how they obtain the integral operator from their derivative operator is by replacing the order q with negative q. Okay, and so we know that the Gruner-Lethnikov formalism is equivalent to the Riemann-Liouville formalism. Okay, it can be shown. but the proof is very long, so we're going to go through on to our next topic. So we want to show something similar to which we just saw, and that is the connection between Cauchy's integral formula from complex analysis and our definition of the integral operator and derivative operator in the Riemann-Liouville sense. Okay, so suppose we obtain our fractional order derivative operator by replacing the order in the Riemann-Liouville integral operator with negative alpha, so that we denote differentiation. Okay, we reconcile this with Cauchy's complex integral formula by replacing this factorial with the gamma correspondent and deforming this contour C into the Hankel contour, right? So what this contour does, it rotates the contour with winding number 1 in the clockwise direction, so that we get a result where the expression in gamma is negative q. Okay, so through a couple of steps here, what we did here is we factorized e to the pi I, then together with the 2I, we obtained the complex sine q plus 1 pi, and we rewrite e to the negative I pi I, substituted with Euler's identity, which is equal to negative 1, and then we again use Euler's symmetry formula to show that gamma of q plus 1 is equal to, well, together with this whole negative 1 and stuff, is equals to 1 over gamma of negative q. Okay, so that is pretty interesting result. Then we talk about the Laplace transform. So what we would like to mention is that we could have defined the integral operator in terms of the Laplace transform as well. Okay, so there's yet another approach to have done this development. So what we could have done is to write j to the alpha of f of t, the inverse Laplace transform of 1 over s to the alpha of the Laplace transform of f of t, where this s is a complex number, sigma plus I omega. So basically we transform this to the frequency domain and back into the time domain. Okay, that result can be easily obtained by using the convolution product, and it is used as an alternative for computation. So basically here we quickly compute the alpha order integral of the power function t to the lambda, and in the 3 steps you can see we have obtained the result, which is a much quicker way as opposed to using the Riemann-Liouville definition in some ways. So we talk about the Taylor series. Remember before we've mentioned that the Caputo formalism of the derivative operator takes the non-integer order integral to the left of the derivative, in which case it produces these transient terms and provides us with a clue of how to define the Taylor series. So this is our definition of the Taylor series of a function centered at a point, our fractional Taylor series. And so you can see in our definition, in the summation sign, we have the derivative applied first, and then we have the integral. Okay, and we also mentioned that k here need not be an integer number. Okay, we'll also mention something about f of a, and so we will mention why f of a cannot be included in the summation term. So let's quickly look at this next thing. We can see that that formula is equivalent to this formula, which is given on the slides, the handouts that I've given you individually. So you can see that we can pull out this term, because if we evaluate them at a certain point, they are constant. Okay, so f of a cannot be included in the summation because this requires evaluation of gamma 0, which is undefined. Okay, so we cannot include that, but we're going to demonstrate the power for this fractional Taylor series by applying it to the binomial expression x plus y to the n. Okay, about the point a equals 0. So first thing we must do is to compute f of 0, and we get that easily. We just substitute 0 in x, and then we compute the kth order derivative of x plus y to the n and evaluate that at a equals 0. We obtain this expression with gamma coefficients. Okay, so if we substitute these two results into the generalized fractional Taylor series formula, we can easily reconcile it with our classical definition of the binomial expansion formula. Okay, we can also illustrate some neat examples of the exponent function, the sine x function and cos function as well, even starting at non-integer summation. But for sake of brevity and completion of the discussion, I'm just going to continue for now. So one application of the fractional calculus is to solve the total current problem in a much simpler way. Okay, so the total current problem requires to determine the shape of the curve, okay, which requires the shortest amount of time or the least amount of time for a particle to slide from a arbitrary position to its lowest point, okay, or to lowest potential in a sense. So Abel was the first to solve this problem through the use of classical physics, in which he set up a differential equation, did a Laplace transform, did convolution products and inverse Laplace transforms, and lots of integral computations, which we can bypass if we notice that we could obtain the same result by applying the semi-integral operator to the arc length derivative sigma 1, and then we can most immediately obtain the Abel solution for the total current problem. Okay, so this is useful because this avoids the Laplace transform and convolution and inverse Laplacing, and it also avoids the complicated integral evaluations. So the next thing we're looking at is the future directions and where we're aiming to go with the fractional calculus in the next couple of years. And so basically, if you recall from Fredholm theory, it is concerned with solving operator equations in the generalized norm spaces and providing certain criteria under which these operator equations are or do provide solutions. Okay, so we would like to raise the questions of whether there are analogous or similar criteria that we could develop that would help us solve non-integer order operator equations, and talk more about that later. But we believe that a reasonable starting point for tackling this problem would be to start with the sequence spaces P and LQ and do inspection on the duality between these sequence spaces by refuting the Hilder conjugate relation between P and Q, and rather coming up with a new relation between the two spaces. Okay, and from there reworking our way through the solvability theory on operator equations. Okay, so thank you for watching. This is a really interesting topic. I really enjoyed talking about it. So if you have anything to add, feel free to comment or leave a comment in the boxes below, or even if you have any information you'd like to share with me or ask any question, feel free. I'm more than willing to help and correspond. Thanks for watching.